Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. We think we've got another great topic for you today on our Tuesday live stream. Today's topic is OCS as an Ethernet IP I/O adapter. So if you're an OEM that is using OCS as your machine control, or maybe you're an OEM who normally uses Rockwell, and you're looking for a more available option in a Horner OCS, in both of those cases, you may be looking to make sure that your machine has the ability to exchange Ethernet IP data with your customer, your end user customers, Rockwell CPU. So in both of those scenarios, today's topic should be great for you. All right, since we are fully live, I'm going to go ahead and bring in my colleague, Mr. Casey Gardner. Hey, Casey, how we doing?
Hey, not too bad. How's it going, Chuck?
It's going great. Now, certainly one way in which an OEM machine builder can add value to their machine is by improving its connectivity.
Yeah, absolutely. So very common protocols like Ethernet IP or Modbus TCP in the Ethernet world are really common to just enable and have a kind of standard address or amount of variables that are kind of open to the network, just to be able to share that kind of data with the appropriate systems on the network for that matter.
Absolutely. So if you're talking about Ethernet IP, it's probably going to be, a Rockwell CPU for the end user's PLC on a production line or something. If you're talking Modbus TCP, you could be talking a Modicon PLC, or you could be talking just a SCADA package talking Modbus TCP. So lots of options there for OEM machine builders. Today, though, it's all about Ethernet IP. Okay, so we are fully live today. So Casey is manning the chat. If you have a question and you're watching this live, go ahead and give that to us in the chat section. If you're watching this on replay, we'll still want your questions, but go ahead and give those to us in the comment section. Okay, let's go ahead and get started. Okay, here's how we're going to break down today's topic. We're going to start with a quick review of Ethernet IP. What is Ethernet IP? We're going to talk about different Ethernet IP device classes. There's different types of devices on Ethernet IP. It's good to understand the differences. We're going to talk about different Ethernet IP implementations and which ones really are best for OEMs. We're going to talk about detailed implementation of those Ethernet IP workflows, and we're going to give you examples of those. And then at the end, we're going to show you kind of what the configuration looks like on the Rockwell side of things that your end user will go through to share that data with your machine over Ethernet IP. Now, before we dive into the topic specifically, I do want to mention that we've got a couple other videos you may be interested in. We have an Ethernet IP communications webinar available on our website that took a deep dive into Ethernet IP as a protocol. Also, at the beginning of February of 2022, we did a hands-on with the Horner OCS and the real-time automation Ethernet IP scanner. So that's another one you might want to check out. Again, both of those are available on our website or on our YouTube channel. Now for our quick review of Ethernet IP. So what is Ethernet IP? Well, certainly it's one of the most popular industrial Ethernet protocols available today. It's an open protocol that's managed by an organization called the ODVA. They were originally formed as kind of the manager of the DeviceNet specification, but since that time they have added many other protocols, and Ethernet IP is definitely a prominent one. Now, the reason why Ethernet IP is so popular is largely because of the fact that Rockwell Automation promotes Ethernet IP, and they have, of course, the #1 market share in North America for automation. Now, why is Ethernet IP potentially important to an OEM? Well, certainly, as Casey and I talked about in the open, implementing industrial Ethernet protocols like Ethernet IP or Modbus TCP can improve the connectivity of your machine, and it can make your machine more valuable to your end user. All right, now we're going to start the discussion about Ethernet IP device classes, because there's different types of devices on Ethernet IP, and it's good to have an understanding of what those are. So let's start with what's called an I/O scanner. Now every Ethernet IP network must have an I/O scanner. And most commonly, just because of market share reasons if nothing else, most commonly it's going to be a Rockwell PLC. Now another type of Ethernet IP device class is an explicit message client, and that is typically an HMI. So it's an HMI device, again sharing data, reading and writing data with other devices over Ethernet IP. Next we have a device which is a little more rare, an explicit message server. Really the best example of that would be a barcode scanner that supports Ethernet IP. And then finally, we have the most common device on Ethernet IP, and that is the I/O adapter. That's what we're going to talk about today. That could be an AC drive, it could be a temperature controller, it could be a pneumatic valve, it could be your machine being run by an OCS, and we'll talk about that in a minute. Now first let's talk about the scenario where the OCS is the I/O scanner on the network. So from an OEM perspective, this would really only be valuable if you have an internal Ethernet IP network on your machine and you have devices on that network that will only talk Ethernet IP. Okay, so in this scenario, since the OCS doesn't support I/O scanner directly, you'll need a third-party device, such as one from Real-Time Automation, Hilscher, or HMS. And again, this isn't as useful to OEMs because most of the time they have the option on their equipment to use equipment that supports multiple protocols, such as Modbus TCP. But if this is what you're looking for, then remember I referenced that video earlier in the presentation today, and you can check that one out. Next, let's talk about using the OCS as an explicit message client, as an HMI on an Ethernet IP network. Now that certainly is viable in general, but that's really more popular for end users because it's usually end users that want to add an HMI to their system that is an Ethernet IP based system, and in order for the OCS to access tags on a Rockwell PLC, for instance, you need to have access to that Rockwell PLC program. And as an OEM, you're not really interested in getting into that level of detail with your customer's equipment. You want to build a machine with a standard data map and ship it and allow your customer just to access that data that you've published. So this isn't also, for an OEM at least, this is not the scenario that they're typically interested in. Finally, the topic for today, and that is using the OCS as an I/O adapter. So this allows you as a machine builder, if you've got an OCS as your machine control, for you to share machine data at high speed as I/O data with your customer's Rockwell PLC. And it's all under the control of your customer. You can just publish your data map and hand it over to your customer. So this is certainly the most common implementation of Ethernet IP by OEMs using OCS as their machine control. When we're using the OCS as an Ethernet IP I/O adapter so that our machine can share data with our end user's PLC, what is the workflow? What's the process we need to go through to make this happen? Well, there's really 4 steps. We need to start by designing a map of the machine data that we want to share. Because we don't want to share everything, obviously, all the data of our machine. We just want certain variables that are appropriate, in our case, to share with our customer. So that's the first step. We need to design a data map. Next, there's some configuration that has to happen on the OCS side as you do your machine development with Cscape. And that is a little bit of configuration to allow the OCS to support Ethernet IP. And it's very little. We'll review it in detail. Next, there's a step involved also in Cscape to map new and existing variables to and from the network. We'll go through that in detail as well. And then finally, you need to update your machine documentation to give your end users the information they need to be able to access that data that you're publishing over Ethernet IP. All right, let's take a look at these steps individually, starting with designing a map of machine data. So what should I include as an OEM machine builder? What data should I publish? What data should I produce? What data should I consume? over the network? Well, of course, it's totally up to you as a machine builder. You can share as much or as little as you'd like. Now, for the data you're going to produce, okay, so this is output data from your machine. You're producing this data. Now, that's considered input assembly data from an Ethernet IP standpoint, because from an Ethernet IP standpoint, the data is always looked at from the perspective of the scanner or the PLC. So your produced data is input assembly data to the PLC. And that can be information such as machine status, alarm information, process variables like temperatures and pressures, those sorts of things. Now, data coming back the other direction, which is considered output assembly data, in other words, data consumed by your machine, that could be things like machine set points, setup parameters, and command information, start command, stop command, that sort of thing. Now, when you take a look at the data you're sharing over Ethernet IP, you need to consider what data types should I support. Well, in general, Ethernet IP supports Boolean, byte, unsigned integer, integer, unsigned double integer, and double integer type data. Now, in general, if you don't need any really large numbers, any values greater than, say, 65,535, then you should be able to use integer data for everything that you produce and consume, for that matter. But what about floating point data, you say? Well, floating point data isn't officially supported by Ethernet IP, but you can support that simply by converting any real data that you have over to integer data with a fixed decimal point. Let me give an example. Let me say you've got a pressure data that you want to share over Ethernet IP, and it's normally between 0 and 100 pounds per square inch, and maybe the current reading that you would be sharing is something like 75.6 psi. Well, you can go ahead and take your floating point data, convert it to a decimal, and say a decimal with an implied decimal point of one place, and 75.6 could be sent over the network as 756. And then when you publish your data map, you can publish the fact that it's in tenth of a pound per square inch instead of whole numbers. So that's one way of overcoming real type data or the lack thereof. Once we've gone ahead and crafted our data map, next we need to go ahead and do a little bit of configuration in Cscape for Ethernet IP. And the steps are shown here on the screen. And we're going to go through those in detail here with a Cscape demo here in a couple minutes. But basically the process is making sure that your Ethernet LAN is configured, because Ethernet IP is an Ethernet protocol, so that LAN has to be configured, things like IP address, net mask, etc. You also need to go through and find on the list of resident protocols that are shown right below the Ethernet configuration. You need to find Ethernet IP on the list and select it. And then with it highlighted, you're going to go ahead and configure the Ethernet IP details, which are going to include things like the source of the data you're going to produce on the network. So again, data you produce to the network from your machine will be seen by your customer's PLC as input assembly data, because it's produced by the machine and received as input data by the PLC. Now, you're going to want to configure this as an integer-based array. And that array size should be equal to the number of words that you're going to produce to the network. Conversely, come in the other direction, you also need a separate variable array of an integer type for the data that you're going to consume. Now next, you need to assign a status variable. And that can either be an integer or it can be a small byte array with a dimension of 2. And the information you can get from the status variable will include the number of I/O connections that are active and the number of explicit connections that are active. And if your customer has your machine connected to their Ethernet IP CPU, then you should see values greater than 1 there. One other note, and that is that you can't produce or consume more than 128 words of data to and from the network. Okay, now that we've gone ahead and configured Cscape for Ethernet IP, Now we need to go ahead and do some mapping. Now, mapping is a feature or a function that really only needs to be performed occasionally with variable-based advanced ladder. It needs to be performed with real-world I/O, and it needs to be performed with network communications. And Ethernet IP is no exception. So the first thing you're going to do is you're going to map your produced data array to an area of internal OCS memory %R, somewhere in that memory structure. On the screen there, I believe I have configured as my produced array register 1000. That's how my mapping has been done on my example on the screen there. And similarly, for the data you're consuming from the network, you also want to take that array that you created and map that also to a different area of %R memory. You just need to make sure that those areas don't overlap. And then you're going to go through a process that I will demonstrate in person here in a minute that will take individual variables that already exist on your machine, or maybe new variables you create for the purposes of communications, and you take those individual variables and you map them into that register space to get them into the area of memory that is either broadcast to the network or that's consumed from the network. And again, we're going to show you that in a first-hand method here shortly. All right, let's dive into Cscape and go through an OEM example application. All right, so before I open Cscape here, let me talk about the example that I've got for you today. So in my very simple example, I'm a manufacturer of a simple sump control from Acme Sump Control. And I want to be able to provide my users, my end users, with the ability to share data with my sump control over Ethernet IP. So again, the first step in that process is to design a data map. What data do I want to share as produced data? What data do I want to share as consumed data? All right, let's go ahead and start with the data I'm going to consume in my example application. So that is data that, from the standpoint of the Ethernet IP CPU in the Rockwell PLC, for example, that is going to be output data. So it's output from the PLC's perspective, and it's consumed by my machine, by my OCS on Ethernet IP. So what I've done there is I've mapped out 5 words of data that I want to consume. The first one is what I'm calling a control word. So that is a bit-mapped word of data that so far only has 3 bits mapped to it for things like e-stop is okay, also a remote start signal, and a remote stop signal. So my first word is a control word that I'm consuming, outputs from the PLC. And then after that, I've got a target well level for my sump level, maximum starts per hour that I'm going to allow on my sump, maximum pump speed, and minimum pump speed. So those are the 5 words I'm going to consume in my example. Similarly, I've mapped out the data that I want to share, that I want to produce to the network, that's going to be seen as input data to the Rockwell PLC. So I've got a status word of bit-mapped information, and so far I've just got whether my sump is in auto mode or not. The next bit is whether my pump is running or not. Okay, and then the other data that I'm going to produce includes the current well level, as well as the number of starts for my sump in the past hour, as well as my current speed. Okay, so that's the data map that I've created for my machine, which is a sump control. Now let's go ahead and go to step 2 and 3, which is to configure Cscape, and then also to map variables in Cscape. So now we'll go ahead and fire up Cscape. And we're going to start in the hardware configuration. All right, so I'm going to pull up the hardware configuration, go to my LAN 1 config, and I need to make sure that my Ethernet or my LAN 1 is fully configured. Okay, so I've got variables assigned for IP address, net mask, etc. So all my normal configuration that I would do for any Ethernet protocol is all done and complete, because that is a prerequisite for configuring Ethernet IP. Next on my list of resident protocols, I find Ethernet IP, make sure it's checked and highlighted, and then I press Configure Selected Protocol. Okay, now here is my produced data I'm sending to the network that is seen as input data to the PLC. So I've created a word array, an integer array variable that has a total of 4 words that's called EIP underscore produced. And I'm basically pointing at the first member of that array. On the consumed side of things, I've got a separate integer-based array called EIP consumed. Again, the names don't matter, it's just what I've chosen to use. And then that particular case of consumption of data based on my memory map or my data map that I previously showed you is I'm going to be consuming 5 words. And then I also have Ethernet IP status that I need to configure. It could either be a word, or in my case, I've decided to use a byte array with a dimension of 2. The reason I chose that is because the information in the status is actually the lower byte tells me one thing and the upper byte tells me something else, so it's more convenient to use a byte-based array in that case. Okay, so that's all the configuration that's required for my Ethernet IP network. Next, we get to the data mapping. Now, I'm going to briefly go back to the slides and take a look at my predefined data map before I dive into the next mapping portion of the configuration. So you can see there that, again, I have 5 words I'm consuming and 4 words I'm producing. So let's go back to Cscape and let's pull up our program variables table here. Okay, and let's take a look at that produced array and that consumed array. And let's start with the produced array. All right, so it's integer type with the proper size that matches the amount of data I'm producing or consuming. And this is that step of memory mapping I talked about. So the data I'm producing, I just had to find an open area somewhere in %R register space. I chose an even number, R1000, to keep it simple. So those 4 words of produced data will be mapped starting at R1000, and they're going to go to R1003. Now, for my consumed data, I just need to make sure it didn't overlap with R1000, and obviously it's not going to overlap since I started it at 2000. So 2000 through R2004 will be mapped for the data that I'm consuming from the network. So that was the first step I had to take. Now, next what I do is for the data that I am producing, I need to one by one map variables that I'm going to produce to the network, and I need to map those to the appropriate locations in memory. So let's go ahead and take a look at that. So let's go down here. The first thing I'm producing is my status word. So I mapped that to the start of my array, which is at R1000. And then if I go back to my map, you can see at the bottom there the order of the data that I've determined. So now in order, I go ahead and map my well level to 1001, starts last hour to 1002, and pump speed to 1003. So that's the data that I'm producing. Next, I have to map my consumed data. And again, quickly going back to my slides and looking at the top to see the order in which I have mapped out my particular consumed data. I start with the control word, map to 2000, and move on to the target well level, the max starts per hour, the max pump speed, and the minimum pump speed, as you can see, are all mapped in order there. Okay, so that's the mapping process that I do. And again, it's only required because this data is going out over the network, and I need to be able to tie my produced and consumed integer arrays to individual variables. All right, now one thing you'll notice that you didn't see here on my variable table is you didn't see those bitmapped bits that were part of my status word and my control word. So let's take a look at how I chose to handle those. So I've got a little section of logic called network in here, where I've taken data from the control word, that is the bitmap data. And remember, of those 16 bits in the control word, I'd only actually mapped 3 of them. So for the first 3 bits, I've mapped them over to internal variables in my program, one called net estop OK, another one called net remote start, and another one called net remote stop. So I just chose to use a simple rung to go ahead and map, again, control word data coming in from my array to basically my output coils. All right, so let's take a look at that. Well, actually, that's pretty much all the details that you would need there. Now let's take a look at data going out for those individual bits that are going out. So my auto mode status goes from an internal variable to the first bit of the status word, and my pump run status goes from an internal variable to the second bit of my status word. Next, let's talk a little bit about the fact that I mentioned that we don't necessarily have floating point data we want to send to the network, but we have data that is decimal or integer type with a fixed decimal place. So let's talk about that. Let's say, for the sake of argument, and in my example, I have my well level that I want to go ahead and send to the network and produce. That, let's say internally in my program, let's say that's a real value. And I'm not going to send that out directly over the network, but I want to send that out in, say, tenths of an inch. So in that scenario, what I'm going to do is I'm going to take my real value, which is my internal variable, multiply it by 10 so that I now have a real value in tenths of an inch, and then I'm going to convert from real to integer, and then the current well level variable is going to contain now my well level in tenths of an inch, and you'll notice that current well level is down here, and it's part of my produced array of data. So that's the step of actually using a little bit of logic to take data that I'm consuming and map it to internal variables, and then to take data that I want to produce and copy it over from internal variables to my variables that are sent out over the network. Let's head back to our slides now and take a look at the last step of the process. Okay, and that is we need to publish our data map in our user documentation. And it's really the same information that you see in the center there, with the additional information that you need to let your user know that when they go on the Rockwell side to do the configuration on the Ethernet IP side, that the output assembly number that they have to have in order to successfully talk to the OCS as an Ethernet IP I/O adapter, the output assembly is number 100, the input assembly is number 101, and the configuration assembly is number 3. And then you need to also have the appropriate data sizes as well. Remember that our input assembly from a PLC standpoint is going to be 4 in my example, and the output assembly from a PLC standpoint is going to be 5. All right, now let's go ahead and show what the configuration will look like from a end user perspective that's using Rockwell tools such as RS Logic 5000 software to adjust their CPU, their Rockwell CPU, to exchange data with your machine. So I do apologize. I actually have RS Logic 5000 software, but the computer it's running on has died. And we're in the process of getting it transferred over to another computer. And I'm not knocking Rockwell, but I'm just saying that it's not a simple process to do that transfer. So I didn't get it done in time for today's webinar. But basically, I've got screenshots for you to give you all the details. So again, from I/O configuration in RS Logic 5000, you're going to right-click under Ethernet, hit Add Module. You're going to go through and find generic Ethernet module from the list of Rockwell options. Next, you're going to go ahead and fill in just a convenient name for your machine, or the customer is going to fill in a convenient name for your machine under a description. In this case, I use sump control. They can fill in a comment if they like. And then they need to fill in those assembly instance details. And that was that additional information that you need to publish that I showed on the last slide with the input assembly instance number and the proper size. In our example, it's 4. The output assembly instance and its proper size, which in this case, the size-wise is 5. And then the configuration assembly instance for your machine based on a Horner OCS is going to be 3, with a size always equal to 0. Once you've configured that, it's just a matter of setting a couple more things, or your end user will set a couple more things, and that is they'll set a requested packet interval to set the update rate, which can be as fast as every 10 milliseconds. And then they also need to make sure that they select the use unicast connection, that option is selected. Okay, so that's really all it takes from a configuration standpoint on the Rockwell side of things. And then automatically there will be IO tags created for all of your data that's in your machine. Okay, so that wraps up the material that I wanted to share with you today on turning your OEM machine into a device that can share data over Ethernet IP. So I'm going to go ahead and bring Casey back in. Okay, Casey, did I miss anything?
Not that I could tell, and I don't see any questions coming in either. So
okay, very good. And once again, if you're watching this on replay, go ahead and give us your questions in the comment section and we'll get those answered quickly. Thanks, Casey. Just a reminder, we have YouTube every Tuesday at 2 o'clock. If we're not live, we'll stream live to you a pre-recorded video like we did last week. And next week, we've got a great topic for you, and that is we're going to talk all about the Horner X5, which is a unique all-in-one controller. It has unique capabilities, and it's just one that doesn't get enough attention. So I thought it was important that we spend a little time with the X5 next Tuesday at 2 o'clock. And as we close, I do want to remind you, if you haven't done so already, please consider subscribing to our channel. And if you do, of course, it doesn't cost anything. And if you choose notifications, you'll have an opportunity to be notified every time we go live or every time we post a new video. All right. Thanks for joining us today for our Tuesday topic, and stay safe out there.